In this video, we're going to look at another example of volumes by slicing. The question here is to find the volume of a pyramid with height h, whose base is an equilateral triangle with side A. The first step is to draw a picture of the solid and a cross-sectional slice. So looking at the solid, you can see how the cross-section at the bottom is an equilateral triangle, and these cross-sections get progressively smaller in area as we go up the pyramid. So, the challenge here is to find the cross-sectional slice as a function of the direction in which we will add them. Let's draw a two-dimensional version of this solid and place it on an xy coordinate system. So you can see how the origin is at the center of the base of the equilateral triangle, and we have a cross-sectional slice with the base PQ. There it is. And this cross-sectional slice is going to be equilateral triangles. All the cross-sectional slices are going to be equilateral triangles. And you can see how this triangular slice is going to be coming out of the screen, basically. So it's kind of like this, like that. And we're going to add up all of these cross-sectional slices. And that gives us the volume of the pyramid. So the distance from the line segment PQ to the origin is, of course, y. And the distance from the top vertex of the pyramid, which is h, to the line segment is, of course, h minus y, because we're on the coordinate system. And there it is. This is x here, and this is x. The whole length of PQ is 2x. It's equilateral triangle. That means all the sides are of equal length. That's 2x. That's 2x. And we're going to create a 30, 60, 90 triangle out of this. All right, let's do that on the next page. So the cross-sectional slice at height y is an equilateral triangle with side length PQ is equal to 2x. So we've drawn a typical slice, and you can see how the base is the base has a length of 2x. The height bisects it, so it's going to be x here. And we get a 30, 60, 90 triangle, because if you have equilateral triangles, all sides are equal. It means all the angles are equal, and the angles add up to 180. So each of the angle is going to be 60 degrees. But the height bisects the angle, and we're going to get 30 degrees here, pi over 6. So now we have the 1√3² triangle. So if this length is x, then the length of the height, which is the side that's opposite 60 degrees, is going to be √3 times x, √3x. That's because of the 1√3² triangle. The smallest angle is 30 degrees, pi over 6. That's opposite the smallest side, which is 1. The medium angle, which is 60, is opposite the medium side, which is √3. And, of course, the largest angle, which is 90, and that's opposite the largest side, which is 2. All right, so the key concept is that the area slice, the cross-sectional slice at height y, is perpendicular to the y-axis. So we need to find the cross-sectional area as a function of y and integrate in the y direction. That's what the integral does. It adds it up. And add up the horizontal equilateral area slices in the direction of the y-axis to obtain the volume. All right, so the challenge here is to find a formula for the cross-sectional slice as a function of y. So the slice area is going to be 1/2 the base. The base has a length of 2x times the height, which we found to be x √3 from the 30, 60, 90 triangle. The 2 cancels with a 2 here, so we get √3 x squared. But we need the slice area, the cross-sectional slice, to be a function of y, not x. So let's apply similar triangles to express x as a function of y. By similar triangles, we're going to get h minus y, ratio of corresponding sides are equal. So we have h minus y, so here's h minus y, divided by x is equal to the whole length, which is h, divided by this length here, a over 2. So ratio of corresponding sides are equal. In fact, let me split up these triangles so you've seen this, just so it's clear, because sometimes students get confused with this similar triangle setup. So let's do it. We have h minus y. If we split up these triangles, there's 90 degrees. Then the bigger triangle is like this. Its length is height. That's its height. We have a over 2 here. And there's the hypotenuse. So ratio of corresponding sides are equal. That means h minus y divided by x is equal to h divided by a over 2. By the way, you can write this in any order. You can write it as long as it's consistent. So h minus y divided by h is equal to x divided by a over 2. As long as you're looking at, as long as you're equating ratio of corresponding sides. So ratio of corresponding sides are equal. We need to find the cross-sectional slice as a function of y, then add them up in the y direction. All right, so the slice area is equal to root 3 times x squared. We applied similar triangles to obtain h minus y divided by x is equal to h divided by a over 2. Rearranging this and solving for x, isolating for x, we get x is equal to a over 2 times h minus y divided by h. So the cross-sectional slice a of y, which is root 3x squared, we need to make this a function of y so we can integrate in the y direction, so we can integrate with respect to the variable y. So we get root 3, but we have solved for x in terms of y right here. So root 3 times a over 2 times h minus y over h all squared. If we simplify this, we're going to get root 3 a squared over 4 h squared times h minus y all squared. So we have a of y, the cross-sectional slice as a function of y, the cross-sectional slice of one of the equilateral triangles, and these slices are of course perpendicular to the y-axis. We're going to integrate them in the y direction. Root 3 a squared divided by, put all the constants in the front for a squared, this makes it easier to integrate, times h minus y all squared. Now that we have found the cross-sectional area slice a of y, this will form the integrand of the volume formula. So the volume is given by integral from c to d, these are y values from c to d, a of y dy, where a is equal to, c is equal to 0, d is equal to h, the upper y value, and the cross-sectional slice as a function of y is root 3 a squared over 4h squared times h minus y all squared. All right, let's now do the integration. Integrate the area slice a of y to find the total volume of this pyramid. So volume is integral from c to d, a of y dy, c is equal to 0, the lower y value of integration, d is equal to h, and the cross-sectional slice a of y is equal to root 3 a squared over 4h squared times h minus y all squared. So the volume is integral from 0 to h root 3 a squared over 4h squared times h minus y squared dy. Now all of this is a constant. Root 3 a squared over 4h squared is a constant. It passes right through the integral. Anything that doesn't have the letter y in it is a constant because we're integrating with respect to y. So that passes right through the integral, and we're going to get root 3 a squared over 4h squared integral from 0 to h minus y all squared. Now we can certainly open up this integrand and integrate term by term and reverse the power rule, but let's do something different. Let's apply the U substitution so we get some practice with U substitution technique. We're going to let U be equal to h minus y du, the derivative of both sides is minus dy. We're applying U substitution. All right, so we're going to get volume is equal to root 3 a squared over 4h squared. Applying U substitution, we're going to get h minus y all cubed divided by minus 3. Don't forget the minus. The minus is coming from the fact that the derivative du is minus dy. Evaluated from 0 to h. Now apply fundamental theorem of calculus, because volume is equal to, let's put a minus in the numerator, minus root 3 a squared over 4h squared 4 times 3, that's 12. So let me write this as 12h squared times h minus y cubed, evaluated from 0 to h. So we get minus root 3 a squared over 12h squared. Now apply the fundamental theorem of calculus, put the upper limit in, we get h goes into y, we get h minus h, that's 0, 0 cubed, that's 0, so 0 cubed, minus, now put y equals 0, plug y equals 0, we get h minus 0 all cubed minus h cubed. And if we simplify, we get minus root 3a squared times minus h cubed. The volume, after simplification, becomes root 3 a squared h cubed divided by 12h squared. Well, now h squared cancels with h cubed, giving us h. So we get volume as root 3 a squared h divided by 12. This is the volume of the pyramid with the equilateral base and equilateral cross sections. All right, thanks.